All right. Well, happy Thanksgiving, Alex. Thank you for turning in that last assignment. We're going to continue looking at the relationship in quantitative data. And on the last assignment, if you look at some of my comments, you might have had a scatter plot and, oh, geez, that's not what I wanted to happen. You might have had a scatter plot. Let's see if I can get, this is going to look terrible, sorry. And perhaps the relationship, kind of is like this. And you're probably a little bit confused, like, is this moderate? Is it fairly weak, etc.? What is the strength of that relationship? Well, the good news today is we're going to come up with a statistic called the correlation coefficient that is going to be this measurement of how strong the linear relationship is in a set of quantitative data. So if you look at the definition here in the green box, the correlation coefficient, for whatever reason, they have decided that the correlation coefficient's symbol should be lowercase r. And what it measures is specifically the strength and direction of a linear relationship between two quantitative variables. Okay. Specifically now, facts about the correlation coefficient that are really important to know is it can only be a number in the interval of -1 to 1, and I'll explain to you what different numbers represent in that interval. But when the relationship is negative, the correlation coefficient is also negative. And if the relationship is positive, the correlation coefficient is also positive. If the correlation coefficient coincidentally happens to be equal to +1 or -1, which are the extreme ends of the interval in which correlation can appear, the only way that happens is if the dots are perfectly in a straight line. The closer the correlation coefficient gets to 0, the less linear relationship there happens to be. So here are some computer-generated scatter plots with different correlation coefficient values. So if I were to adjust this and maybe make a number line here from the smallest the correlation coefficient can be is -1, the largest the correlation coefficient can be is +1, smack dab in the middle of that is 0. We talked about how if correlation is exactly -1 or exactly +1, that means the dots are perfectly linear. They either just have a negative slope or a positive slope. So if you look at this scatter plot, the one on the bottom right, that has a correlation coefficient of -0.99 because these dots are extremely close to all being on the same straight line. Next to that, a correlation of +0.9. So those dots, you notice, have a little bit of scatter, but they're clearly in a linear pattern. Now, if the correlation is +0.9 or if the correlation is -0.9, I'm typically going to call any correlation coefficient in the 0.9s, whether it's +0.9 or -0.9. We can now quantify that the linear relationship in that data is very strong. Once you get down to correlations of +0.8 or -0.8, in this interval, I'm going to say that those are just strong linear associations. Then -0.7, +0.7, anything in the 0.7s, I'm basically going to be calling fairly strong in their linear relationship. When you get down to a correlation in the 0.6s or so, now we're starting to tend a little bit towards weakness. So that might refer to as moderately strong. Then when you get down to correlations of 0.5, 0.4, 0.3, 0.2, 0.1, we're continuing to get weaker and weaker and weaker. So pretty much anytime the correlation coefficient is down here, it's going to be weak, to very weak in its linear association. And maybe in the 0.5s and 0.6s, it's starting to get perhaps slightly weak in its linear association. So you can sort of see in the pictures above, correlation of 0.5, there's still a clear positive association there. It's just the dots are not obviously in a straight line. The correlation next to that of -0.3, again, the relationship there is negative, clearly. But the straight line pattern isn't obvious. Then on this one where the correlation's 0, Notice there's no obvious linear pattern. I wouldn't be able to tell if the line of best fit is horizontal, diagonal, vertical, etc. And that's literally what it means for there to be no linear relationship in the data. Right? If you want to go to that website, you can, and that just allows you to guess at what correlation coefficients are. I don't think it's really worth your time, though, to be honest with you. All right, if we look at this relationship, manatees or sea cows, they live in Florida, off the coast of Florida. And a lot of times, because they're slow moving, they get hit by speedboats. And a lot of times they get hit and killed by speedboats. So the scatter plot shown here gives us the number of boats registered in Florida, measured in thousands. And the vertical scale is the number of manatees killed in a particular year. And this data spans years 1977 to 2014. Okay. What about this? Oh, yes. So for the problem above, this is what they wanted us to do here. For each of the following relationships is R greater than 0 or less than 0, closer to 0, or closer to plus or minus 1. So on this one, we definitely know the correlation coefficient is greater than 0 because there's definitely a positive relationship in that data. The more boats there were, the more dead manatees there were. Now, is this close to 0 or close to 1? I'm going to guess that R here is much closer to positive 1. I'm going to guess R there is probably somewhere around like a 0.9 or so, because it does look like those dots are very strongly forming a linear relationship in that data. On part B here, does the row in which you sit in affect the test score? So some might think the closer you sit to the front of the room, the better you're going to do on a particular test. So this particular teacher used row as the explanatory variable and the score they got on the most recent test as the response variable. Now, in this one, is the correlation coefficient positive? Is the correlation coefficient negative? Well, for me, it does seem like the overall trend might slightly be negative. So I'm going to choose that one because there does seem to be a very slight overall negative slope or negative relationship in that data. But do those dots form a straight line pattern, an obvious straight line pattern? I think we'd agree no. There's a lot of variability here. So here, this value of R is going to be pretty close to 0. If I was estimating the correlation coefficient here, I'd say the correlation coefficient here is maybe like negative 0.2 or something like that. All right, so how to interpret a correlation coefficient? Here is some data that you've seen in the past. This is how fast does someone run in the, I think it was a 40-yard dash, and then how long is their long jump distance measured in inches. And so what the relationship here says is as the dash time gets bigger, which means the person is slower in the 40-yard dash, that means their long jump distance is going down, right? That means they're jumping a shorter distance. And that seems to make sense to me that the slower the person, the smaller they're going to be able, or the shorter they'll jump because they're less athletic, you could argue. Okay? Now, in this case, some computer technology or calculator technology has calculated this correlation coefficient here to be negative 0.838. Okay, we'll talk about how to get that number in a minute, but it's always going to come from technology. We're not going to do it by hand. But what are we going to do with this? We still want to now allow this to assess the strength. On the previous assignment, remember, we wanted you to address when we talk about a scatter plot, strength, direction, form, and of course, we always want to put this in the context of the problem. And if there are any outliers, we can address that also. So a correlation of negative 0.8, now I don't have to look at that scatter plot and guess as to whether or not that's slightly weak, fairly strong, moderately strong, etc. I now have this measurement that the correlation is in the 0.8s. So for me, I can now confidently say that we do have a strong negative linear association between dash time and long jump distance. And it takes the guesswork out of having to figure out what that strength of the relationship is. That's why we appreciate this correlation coefficient statistic so much. Okay. Now, Mr. W has put in here, warning. If you just get the correlation coefficient value only, you might say, oh, this relationship is totally linear, man. Like it has to be. But that's not true. It's always important to look at a graph of the data because this is the weight of a diamond measured in carats and the price of that diamond. And if you were to put all of these numbers into a calculator or a computer, it's going to spit out a correlation coefficient of 0.93, which if all you saw was the correlation coefficient and didn't see the graph, you'd look at that thing and be like, wow, right? We have a very strong positive straight line relationship in the data. But cool your jets, because what we actually have here is a little bit of exponential growth. So even though the correlation coefficient tells us the relationship is close to linear, our eyeball test tells us that that's best described as curved. So the big idea, make sure you look at the graph of the data. Don't just look at the correlation coefficient alone. And of course, this ongoing theme, just because two things are related does not mean we have one thing causing the other. The only way you can determine causation is if we set up a good randomized comparative experiment, which I don't know if you've talked about or not yet in this class about how to do experiments. Okay, so here's the ridiculous way in which the correlation coefficient is computed. Basically, what this says is you're going to take the first X value. Well, first of all, you're going to have this list of data, your XY data, right, listed in two columns. You're going to have the first X value, the second and the first Y value, all the way down to the last X value and the last Y value. You're going to do one var stats. You're going to, figure out what is the average of your X's and what's the standard deviation of your X's. And then with your Y list, you can do one var stats and get the average of your Y's and the standard deviation of your Y's. Then what you do is this really long-winded computation to get the correlation coefficient. You would take the first XY pair and go up here into the formula and take that first X value, subtract the mean of the X's, divide by the standard deviation of the X's, multiply that by the value of the first Y coordinate minus Y bar divided by the standard deviation of the Y's. And you do that with the second XY pair, the third XY pair, etc. And then you add all those things up, and then you divide by one less than the number of data points there are. So what you're basically doing is multiplying z-scores together and dividing by the degrees of freedom. Now, the good news is you'll never have to know how to do it by hand. You'll just have to know how to get it from technology. Okay, so here's what I would recommend. I'm hoping that you have a TI-84. If not, we'll have to figure out how to do it on a computer website. But hopefully you have a TI-84. You're going to have your X values and your Y values, and you're going to put your X values into L1 of your calculator and the Y values in L2 of your calculator. Okay. Now, there's one setup step after you put the data in, and that is on your calculator, there's a mode button. And what you want to do is hit mode and then go down that menu, and you're going to see something on that menu called Stat Diagnostics down that menu, and make sure Stat Diagnostics are on. For whatever reason, it defaults into the off position when it's a brand new calculator, so you'll just have to do this one time. So once you turn the Stat Diagnostics on, they will remain on forever, basically. So assuming you have the data in L1 and L2, now, to get the correlation coefficient, since your stat diagnostics are on, this command will work. You'll go to Stat button, right arrow over to the Calculate menu. You're going to go down the Calculate menu, and the 8th option on that menu says lin reg A plus BX. Okay, hit Enter, and then your calculator will ask for X list and Y list. Right? And those will almost always be L1 and L2 in there. And then it's going to say like store reg equation, you can just leave this blank. And then there should be a calculate button down at the bottom. And then you should get output. You should get A equals, B equals, R squared equals, and R equals. That R value is what we're focused on right now. That R value is the correlation coefficient. And now all we have to do, instead of calculating it by hand, we just have to interpret what it means. Okay? Important factoids about the correlation coefficient. It makes no distinction between explanatory and response variables. So, if you were looking at the relationship between the length of someone's foot and their height, and you did the calculator command that I showed you above, and for X list, you did L1, and for Y list, you did L2, you'll get the correlation coefficient to come out of that command. But let's say we switched it, and we happen to put height on the horizontal axis and foot length on the vertical. Well, if you switch your X list and Y list in the calculator, the value of the correlation coefficient doesn't change. If there's a relationship between foot length and height, there's also the exact same relationship between height and foot length. Okay, so that's a tricky sort of question. You'll be asked these in like multiple choice questions. Hey, what happens if we flip our axes? How does that affect the correlation coefficient? And the simple answer is it has no effect whatsoever. Okay. The second thing is that if you look at the formula for the correlation coefficient, again, it's a ridiculous formula, but the computations of z-scores don't have units of measure in them. Z-scores are not measured in inches or feet or any of those other things. So, therefore, the correlation coefficient is not changed if the units of measurement are changed. What does that mean? So if we look at the same relationship of foot length measured in centimeters compared to the height measured in centimeters, and let's say you did the conversion, because centimeters are metric system, and us weirdos in the United States use inches and feet and miles and whatnot. So let's say you did the conversion, right? And 1 inch equals like 2.54 centimeters or something like that. I don't even know for certain. But let's say you converted all of the foot length values to be measured in inches and all of the height values to also be measured in inches. How would that impact the correlation coefficient? Not at all. If the correlation coefficient over here was 0.6, the correlation coefficient over here would also be exactly 0.6. Okay? So changing units of measure doesn't matter. If there's a relationship, it exists no matter what units of measure or what country you happen to live in. The relationship exists. Okay? So because of that, the correlation coefficient is also a unitless measure. So when you put out the correlation coefficient value of, like I guess the previous one was 0.6, it's just a number. It's not 0.6 inches. It's not 0.6% or any of those other things. It's just the pure number of 0.6 or whatever the correlation coefficient happens to be. Okay. So this relationship, we've looked at this before, and we talked earlier about how this correlation is negative 0.838, which made it a strong negative linear relationship, and there's not to appear to be any values I'd consider outliers there. Now, what if you switch the x and y values? What if on the horizontal axis you put long jump distance and on the vertical scale you put dash time? How would the correlation coefficient change? Hey, it wouldn't. Okay? There'd be no change in correlation because correlation does not make a distinction between which one's x and which one's y, or which one's explanatory and which one's response. If you switch the long jump distance into feet, how is that going to impact the correlation coefficient? Again, no change in that because it's not impacted by changes of units of measure. Now, if someone claimed the correlation coefficient of negative 0.838 was measured in inches per second, would this be correct? Of course not, no, because there are no units of measure associated with the correlation coefficient. It's literally just the number negative 0.838. How do you deal with outliers? Rather, what effect do they have? You can look at this website if you want to play around with it a little bit, but outliers can increase correlation, outliers can decrease correlation, etc. So this is why it's so important to look at the graph. If I were to cover up those 2 points down there, right, I would say we have a positive correlation here, but it's not super strong, so maybe this correlation is like positive 0.6 or so. Now, if all of a sudden these values down here did appear, the impact of those things is it's actually going to cause the regression line to go towards it. That's going to be the line of best fit now. And so those outliers are very influential on this. Now correlation would be negative. Maybe it's going to be weak. Maybe it's like negative 0.3 or negative 0.2 or something like that. But that's why it's so important to look at the graph, because those outliers right there would make correlation negative, where if you covered those up, the relationship and the rest of the data is positive. Last slide is the correlation of resistance statistic. It says think of the formula. And basically no, right? The correlation coefficient is affected by outliers. And one way an outlier can impact correlation is, say, for example, you have, a scatter plot down here where the relationship is basically 0. Maybe put another dot there. And then if I add in an outlier way out here, okay, now it's going to make this correlation coefficient like positive 0.8, but in reality, the correlation coefficient of just that red swarm down there is basically 0. So yes, correlation is affected by outliers, which means correlation is non-resistant to outliers. Thank you very much. Happy Thanksgiving.